Welcome to the Kyoto Prize at Oxford. I'm Nairi Woods, Dean of the Blavatnik School of Government. And normally, of course, we'd be welcoming you all here in person to our building here at the heart of Oxford. But thanks to each of you for joining us online to celebrate and hear from the 2019 laureates. We'll hear from chemist Ching Tang this morning, from astrophysicist James Gunn this afternoon, and from stage director Ariane Mnouchkine this evening. And at midday, if you can join us, I'll be moderating a more informal conversation with the three laureates. Here's a little clip that introduces you to the Kyoto Prize at Oxford. The Kyoto Prize was founded by Kazuo Inamori in Japan as a prize that would celebrate some of the best achievements in science, in the arts and philosophy, and in technology. It's about 100 million yen, that's nearly $1 million, and it's awarded in Kyoto each year. Kazuo Inamori founded this prize because of his own deep sense that we need to celebrate human achievement that feeds the human spirit. And that's what the prize does each year. It brings together excellence in all of these domains. The Kyoto Prize Laureates have included people like Jane Goodall, known to most people for her work on chimpanzees and primates, Akira Kurosawa, the incredible Japanese filmmaker, or Martha Nussbaum, the extraordinary American political philosopher. Here at the Blavatnik School of Government, we partner with the Kyoto Prize to celebrate it, to bring the Kyoto Prize winners here to the heart of Oxford University, because they enable us not just to hear about the cutting edge of technology, of science, of art and philosophy, but to invite all our colleagues from other parts of Oxford, from Oxford's high schools, from other universities. The Blavatnik School of Government is a department of Oxford University with a mission to improve government around the world. It's to help people learn how to serve, to lead, to govern with a clear sense of who they're serving and why.
For too long, universities have hidden behind an ivory tower, and the commitment of the Blavatnik School is to open up the work of the university to the world around it.
Oxford University is full of brilliant researchers, teachers, students, working on some of the world's biggest challenges. What we love to do at the Blavatnik School is to bring them together with some of the leaders who are making the actual decisions and help be a portal through which all that brilliant research can actually be used and have impact. Every year here at the Blavatnik School, we're delighted to host the Kyoto Prize Lectures. I was so excited to see the latest Kyoto Prize laureates, James Gunn, the astrophysicist, Ariane Mnouchkine, the theatre director, and Ching Tang, whose research brings us things like the OLED screen.
But both Oxford scholars and the Kyoto laureates are animated by a thirst for knowledge, an energy and a commitment always to improve, never to be satisfied. And that's what makes excellence. The University of Oxford is a deeply international institution. We have partnerships across the world. We always have. We accepted our first international student in the year 1169, and we have been welcoming students ever since. The mission of the Kyoto Prize is the very same mission that animated the founders of this university almost 900 years ago. A commitment to excellence, a commitment to using that excellence for the betterment of society.
These values of humility and service, but also of outstanding excellence, are exactly the values that we hope to reinforce in every student that walks through the door. Moderating the first of the Kyoto Prize at Oxford lectures today is Henry Snaith, Professor of Physics here at Oxford. In 2015, ranked one of the world's 2 most influential scientific minds. Professor Henry Snaith in 2018 was the winner of one of the inaugural United Kingdom Blavatnik Science Awards. I'm not going to list all of his other achievements. Instead, I'm going to turn proceedings over now to Professor Henry Snaith. Thank you, Henry.
Thank you, Nairi, for the introduction. So it's my honor and pleasure to introduce our first Kyoto Prize speaker today, Professor Ching Tang. So Professor Ching Tang was born in Hong Kong and moved to Canada after finishing his secondary school education to obtain his bachelor's degree in the University of British Columbia. From there, he moved on to Cornell University and undertook his PhD research in chemistry and graduated in 1975, from where he went to the Eastman Kodak Labs in Rochester, New York. So it was in the Eastman Kodak Labs where the magic happened, so to speak. Kodak were working on the xerographic process of for photocopying and laser printers. And this process originated really from research in the 1950s, but became commercial in the 60s and 70s. And it used organic molecules to absorb light, charge up surfaces or discharge surfaces. And that's the process of xerography, where an ink or a toner sticks to a charged surface. These molecules, these organic molecules, were developed, lots of different ones were developed in Kodak, and they had, in essence, a library of dyes that absorb light, organic semiconductors that could transport charge. So when Professor Tang started in 1975, he was tasked with seeing if he could make useful photovoltaic devices from these materials, and in fact made some key breakthroughs, which I'm sure we'll hear the details of very shortly, that culminated in a two-layer organic heterojunction. He discovered that this organic heterojunction, as well as generating electricity when light absorbed on it, could actually re-emit the light very efficiently. And this discovery of this organic light-emitting diode really starts the sort of modern era in organic electronics and starts the technology that developed into commercial OLEDs. So in the work that originated this stuff, this discovery really took place in around 1975 to 79. But because Professor Tang was working in a company that was more interested, obviously, in the commercial exploitation, he was only allowed to publish this, or the publications came in 1986 and 1987. And I started my PhD in 2001. And by then, these papers had mythical properties. They were the legends of the origin of organic electronics. And one of the measures of impact in the scientific community is how many papers have cited or referenced to this original work. And the 1987 OLED papers attracted more than 18,000 citations. So that means 18,000 separate publications have directly stemmed from this work. And of course, on top of that, there's been a whole tens of patents filed by Ching Tang, and the Kodak and many other companies now developing these technologies commercially in OLED applications. So following his time at Kodak, when Professor Tang retired, he could have just sort of retired and probably enjoyed a very nice retirement, but he was curious to develop science more. So he took on a position at Rochester University of Rochester, and took on the Doris John Cherry Professor of Chemical Engineering. And more recently still, he's taken on a professorship at the Hong Kong University of Science and Technology Jockey Club Institute for Advanced Study. And there he now has these joint appointments between Rochester and Hong Kong. And I believe he spends most of his time more recently in Hong Kong, where he's returning to his motherland. Professor Tang has won a number of awards and accolades, and I won't list them all, but just some of the key accolades and honorary fellowships. He was elected to the Fellowship of the American Physical Society in 1998, and he's a founding member of the Academy of Sciences in Hong Kong. He's won a plethora of other awards, which I won't talk about, because what we're most interested in is his Kyoto Award and his Kyoto Award presentation. So thank you very much, and I'm very much looking forward to hearing your talk, Professor Tang. So I'll hand over to you, and we will enjoy the next half an hour or so of your presentation.
Thank you very much, Henry, for this nice, very kind introductions. I would like to share my slide to begin with. Can you see my slide? Oh, well, first of all, I would like to thank the Inamori Foundations for honoring me with the Kyoto Prize. I would also like to take this opportunity to send my best wishes to Mrs. Kanazawa, the president of the foundations, and her staff in Japan, for the good health. And I also want to thank the Kyoto Prize at Oxford for hosting this event. The title of my talk, that's the evolution of the science of organic light-emitting diodes. As Henry said, I've been at many places. My current institution is Hong Kong University of Science Technology. I was born here in Hong Kong. I spent 31 years at Eastman Kodak Company from 1975 to 2006. And after that, I spent my time in academics in the University of Rochester and here at the Hong Kong UST. Okay, first, a little bit about Hong Kong. This is the map from Google Earth. The Hong Kong is a very small place. There's only 427 square miles total. A little bit of history. In 1984, it was a British colony after the Opium War. And in 1997, it was returned to China as a special administrative region of China. And Hong Kong, like many great cities in the world, is a city of lights. In this photo of Hong Kong, which shows the Victoria Harbor at night, you can see a beautiful panorama of lights from the skyscrapers along the waterfront. If light is a symbol of hope, I would say that light in Hong Kong has been dimmed considerably with the recent events that you might have heard in the news. The situation in Hong Kong is getting more chilling. It is time to stand with our head high. This is a quote from a Hong Kong newspaper publisher who's sitting in jail at this time. I'm hopeful there's light at the end of the tunnel, and I'm here to tell you a story having to do with searching for light. I was born in Yuen Long, which is in the north corner of Hong Kong. It's very close to the border of Hong Kong. Beyond that is the city called Shenzhen. Shenzhen was a small fishing village when it was at the time in 1950s, or 60s, or even the 70s. But it's now grown into a city of almost 13 million people, just right across from the border. But the Hong Kong, the place where I was born in 1947, was a really just a bustling small little town about 10 miles from the Hong Kong center. And this is my family home. It's a brick mansion by the British standard. It was built in 1921, almost 100 years ago, and still standing. And this picture here is the British Shrine. I don't know how long ago it was built, but probably about the same vintage as my old house, my family house. It has a one-room school attached to it for the British kids, where I learned to recite, memorize, and to obey rules when I was 5 years old. So a little description about my research career, which was mentioned by Henry. I give a little more detail. In 1967, I left Hong Kong for University of British Columbia. And I did research for 2 summers with Professor Ogrislovs. He's the person who introduced me to scientific research, and I did some chemistry of oxygen excited states, and actually published a paper on it. And then for graduate study, I went to Cornell to study with Professor Andy Albrecht. He taught me more than science. He got me addicted to reading the New York Times. I'm still reading it every single day. I did my thesis on core field photoconductivity. So Andy's specialty was in molecular spectroscopy. So I was a little away from his main field. But that also taught me to be very independent in carrying out my research work. At Kodak, where I spent the bulk of my time from 1975 to 2006, I was hired by this gentleman, Brian Rossiter. He's the director of the chemistry divisions. He is a very inspiring person. He himself had to fight against the Kodak management to start solar cell research. And he hired me to do organic solar cells. And he also helped me with immigrations. Without him, I'd probably be somewhere else. I don't even know whether I would be involved with OLED or not. So for the 30 years, I was a very happy researcher, and so happened I discovered organic photovoltaic and also OLED. So people would ask, what's the difference? LED and OLED, and what are they good for? So for the layman's, I just typed LED in the Google search. So this is the first page that show up, and it all shows the indicator light bulbs, and almost nothing else. And I circle something around here, and that is actually OLED, because I can identify it. It's not LED. So LED is really a point light source from crystalline semiconductors, as distinct from OLED. So I typed OLED in the search term, and that's what I got. It's all TVs, smartphones, laptops, etc. So OLED is categorized as an area light source. It's made with thin films, organic semiconductors. So for the LED, these 3 gentlemen earned the Nobel Prize in 2014 for the invention of efficient blue light emitting diode, which has enabled bright and energy-saving white light sources. And then for the organic side, it's not organic LED that they won the Nobel Prize for, but they won the Nobel Prize for the discovery of and development of conductive polymers. These 3 gentlemen, Alan Heger, McDermott, and Sorakawa, they accidentally discovered that polyacetylene, when it's doped incorrectly, it would give you metallic behavior. In fact, the work on conducting organic materials have been done much prior than that. So this is the work, this is the Professor Hinoguchi. He won the Kyoto Prize in 2007, but his work on organic dark conductors was as early as 1954 in his classic paper of doping pearline with bromines. So he was awarded for pioneering and fundamental contribution to organic molecular electronics. So prior to my work on organic light-emitting diode, organic solar cells, there's a whole history of dark conductors, which turned out to be scientifically very interesting, but technologically was not as significant. So here I list in this table what are the most significant organic-based electronic and optoelectronic device that has a tremendous commercial impact, and some of them don't. So liquid crystal is one. The space of the property is basically acting like an insulator. It's a dielectrics. An organic photoconductor, you need to have a very good dark insulations and some photosensitivity is used for electrophotography. Liquid crystal have over $100 billion in the market values. And the organic photoconductor probably approaching that, I don't know for sure, but it's a large number. And for the organic semiconductors, which is based on weak electron donor acceptor interactions, you have application like OLED, OPV, and organic thin film transistors for circuits. You can look at the impact here. The organic LED today has close to $30 billion in market values. Organic photovoltaic, probably less than 10 million. This is not 100 million. And the organic TFT so far has not been commercialized, have been commercialized, but have very little impact so far. As far as the dark conductor goes, it's based on the strong electron donor and acceptor interactions. It's a metallic property. It's used for anti-stack, for electrodes, maybe for battery. And I really do not know what is the commercial value at this point. So, as Henry said, I have published a few papers, and one in 1986, which was based on the two-layer organic solar cells. The other one in 1987 was organic electroluminescent diodes, and the third one was the electroluminescence of a dope organic thin film for color. And Henry quoted like a 16,000 citation for this paper. I think it was a little overstated. But I'm quite happy with 12,000. So let me just go through the discovery phase a little bit, and then I move on to the display applications. So it started with organic photoconductors, the work on electrophotography, and which led to the organic heterojunctions, which leading to the photovoltaic and organic limiting diodes. So this machine, the Xerox 914, is a classic. It actually was started in 1954. That's quite amazing when I saw this number here, this year. But anyway, the engine, the key engine is the photoconductor belt, which go around here. And then the photoconductor is charged by here, and then it get exposed and get developed by using toners, and then if you fix it, and the paper comes out from here. So the photoconductor is the key because you have to be able to sense to do the imaging. Today, Kodak is still in this business, using photoconductors, organic photoconductors, and also all today's laser printers are based on photoconductors. They use drums, and also mostly are organic based. So it's a huge business, from big and to small. So a little bit about the photoconductors, and this is the key. In about 1970s, 30s, 70s, Kodak started this photoconductor research. There's a whole division devoted to that. And we call it the aggregate photoconductor. Basically, it's the bulk heterojunctions, but we didn't call it that way. You can, in the electron micrograph, there's a mixture of three materials: the dye, a whole transport material, amine, and a polymer. You just mix it together and you cast it as a film. Depending on the casting conditions, or you can vapor treat it, it would turn into a so-called aggregate film. You can see, it can identify the filaments running across the film. And you also identify the amorphous phase, which is continuous. So this aggregate phase, which is the dye, with some polymer, form the electron transport phase. And this one here, the amine plus the polymer, form the amorphous phase. So this is it. I mean, the whole industry, the Kodak, the photoconductor, is based on that. So I use that photoconductor not for electrophotographic applications. I was the only person in Kodak working on solar cells. So I learned about this photoconductor. I said, let me use it for solar cells. And this is one of the cells that I made with ITO. ITO is the indium tin oxide, and indium as the electrodes, sandwiching the photoconductors. And you make the photoconductor very thin so that you can pass charge through it. And this is the so-called IV characteristics. For those who are familiar with solar cells, they immediately recognize that this is a very poor performance solar cells. The efficiency is roughly about 0.2%, and the fuel factor is 25%. This is classic that of a forced organic solar cells, a straight line IV characteristics. So the poor fuel factor, I learned, is due to the field-dependent charge generations. Unless you risk the high field, the charge generation efficiency is poor, also the fuel factor is poor. It's a typical of organic solar cell in those days. And the open circuit voltage at this point right here is strictly dependent on the difference in the work function of the two electrodes, sandwiching. So that was the beginning. I spent maybe a year struggling with this, but this is probably the best I could get with the single layer devices. And well, about a year later, I somehow put together a two-layer system with copper ferrocyanide, which is deposited by vapor depositions, and also a dye, which is this. We call it the premium dyes. You have different the heteroatoms, oxygen, sulfur, and so on. The chemists provide this. And with this structure, a bilayer structure, all of a sudden, I find a solar cell which beginning to look like a solar cell with some curvature to it. And the efficiency more or less doubled, but most remarkably, the fuel factor now improved to about 45%. And more importantly, by making the solar cell with this bunch of materials on top of the copper ferrocyanide, I can correlate the open circuit voltages with the HOMO and NUMO, which is the energy of the electronic energy of the donor interceptors, that is more or less a straight line. So that tells me that the open circuit voltage is no longer depending on the electrode, but depending on the choice of the donor receptors. So this is the beginning of the understanding of the heterojunctions, that the junction between the two-layer organic material and donor and receptor would play the key role in the charge generations in the solar cells. So I worked with it maybe for another year or two, and in 1979, I get a patent issues, but the file was submitted in 1978. I finished all the work in organic solar cell by then. So I gave up research on OPV around 1978, simply because I couldn't find a pathway to efficiency greater than 1%. I'm kind of stuck at that level. And the benchmark thin film PV, for instance, the cadmium telluride that other people in my lab at the time working on, their benchmark efficiency is 10%, and they achieve more than 10%. So for me to keep working on a very poor device is just very discouraging at the time. So I move on. And in this patent, I basically summarize a lot of the material that I use for both donor and receptors. And this turned out to be quite useful even later on in research in the field. So I quit in 1978 no longer working on solar cells, organic solar cells. So the paper that Henry mentioned, that was published in 1986. So it's almost 7 years later after the work was done. In fact, the paper was written in the late 70s. So in this paper here, I described, of course, the best data I got it on organic solar cells. The efficiency now I reached 1%, and the fuel factor is 65%. I use the Kupferfeld cyanide still as the donor, but then I use a very strong absorber, the protein in the emit as a receptor. And with these two materials, and making sure that the layer thickness is thin enough that they do not present enough resistance to impair the cell, I get a very good efficient devices, and particularly the fuel factors. So the key here is that the junction between the donor and the receptor is the key for charge generations. In this case, the exciton generated either in the donor or in the receptor would diffuse towards the junctions where it separates into electron and holes and then move on to the respective electrodes. But there's only one minor problem, and that is the actions or the photoactive regions is right at the junctions. Beyond that, it's not photoactive because the electric field is very slow. So there's no way I could improve the efficiency beyond this 1% with extremely thin films like 60 nanometers. There's not enough absorptions. And that is the end of my research in organic photovoltaic practically. So moving on, luckily there was organic light-emitting diodes. So the first organic light-emitting diode I made in Kodak was again a two-layer structures with the Kupferfeld cyanide borrowing from the solar cells. I deposit a electron receptor based on a very highly fluorescent materials called the tetraphenylbutadiene. This molecule was too small to be deposited by vapor depositions. It crystallized. So I mix it with some polystyrene and sprinkle it as a thin film. And this material emits blue light. So this is probably one of the blue light. Well, it's a blue emitting light emitting diode. But the problem there is that the efficiency is not very high. And the bigger problem is that the lifetime is very short. Basically, when you turn on the voltage, you see some light, and then you turn off the voltage, or then you keep the voltage on, the light slowly dissipated. But nevertheless, we apply for a patent for it. When I said that it emits blue light, in fact, years ago, like in the 60s, there were already quite a lot of studies on organic electroluminescence. And this is one of the classic papers that I use all the time to demonstrate that the work in the 60s. And you have the amphicene sandwiched between two electrodes. They use it is a potassium as a cathode, and then the iodine solution as the anodes. And this is very well chosen anode and cathode, and to provide the ohmic contacts. And they demonstrate there's a double injection of the electron and host, and then the recombination near the anode. So therefore, the electrons move across and recombine in this region with the host. And you see the blue light emissions. The efficiency is roughly about 1%. But the key issue here is that the voltage that required to drive this device is very high. It's about 2,000 volts. So even though the efficiency is quite quite remarkable, in practice, it's not very useful as a light emitting device. So here, for 20 years later, here's the paper that we published together with the Stevens light in 1987. And this paper basically They use the same two-layer structure as the solar cells, but with different materials. So the donor now is this amine instead of Kupferfeld cyanide, and the acceptor is the molecule called the ALQ. With these two, the donor and acceptor, having a bilayer structure, again using the ultra-thin organic films, roughly about 50 nanometer each, and couple that with a novel cathode at the time called the magnesium silver alloys, and you get the drive voltage of about 5 volt and a very fast response time on the order of microseconds. And we get a quantum yield just about 1%, just like the paper in the 60s. But we get pretty high brightness. And the problem we had at the time was that the lifetime is relatively short, about 100 hours. Again, in this device, the donor acceptor heterojunction plays the key role. But in this case, it's very different. It doesn't require light absorptions. You want to optimize for the light emissions. And the junction itself is the one that plays the key role, because it's, in this case here, the electron gets blocked here and the hole gets blocked at the junction here. So the recombination is confined at this interface. And therefore, the efficiency, the high efficiency can be achieved by eliminate some of the recombinations at the electrodes. And the other paper that we published, that was 2 years later, a year later, 2 years later, in 1989, was introduced a method to produce color, which is also very simple. That we use the same two-layer structures, but we use a dope layer in the middle, which can be, the host material can be the same as the electron transport layer, but it could be different. And with this structure, you can put some dopants like the coumarin, like DCM. The coumarin will produce the green light, and the DCM will produce the red light. They're using ALQ as the host materials. And it's a very simple gas host, the foster energy transfer mechanism. But this is the scheme that allow you to produce RGBs in organic LEDs. And also is the scheme that can produce high efficiencies as well as lifetimes, because you have the flexibility of a choice of a lot of materials. So today, this is the classic structures that everybody trying to aim at or trying to accomplish, and that is that you have a 5-layer structure, 7 altogether, in fact, including the injection layer. The injection layer is to provide the ohmic contact in both cases. The transport layer is to provide, of course, the transport of the charges. So these can be doped layers, electrically doped, we call, so to increase the conductivity. So this can be the dark conductors, by Higgers and companies. Here, the key is this 3-layer here. One is to block the holes coming from this side, and the other one is to block the electron going from this side. And leaving in the middle a so-called the bipolar transport layer with the doped molecules, the dopants that produce the desired light of particular wavelength. So with this structure, you can optimize the drive voltage through the transport. You can use the particular layer to optimize the layer thickness for the optical couplings. And you can reduce the layer of this one here, or this 3-layer, to make, you can have a latitude to change the layer thickness to optimize the device performance, in other words. So I just want to point out that some of the work that we did, in 87 are still being used today. So the 2-layer structure expanded into the 7-layer structure, but some of the electrode remain somewhat unchanged. So for instance, this magnesium silver that we discovered or we developed in Kodak was still being used for the top emission OLED even in your today's cell phone structures, because these turn out to be one of the best semi-transparent electrodes so far. So going to a little bit into materials, that the blue host material based on the anthracene. You remember this paper that I mentioned in 1965? It's an anthracene. It's a good material with very good quantum efficiency for the blue light. And so we took it in 2001. We published a paper in the APL. We just add two substitution to it. We call this molecule called ADN, and the Jiming Shi is the person responsible for making this material. And with today, the commercial materials are still based on the anthracene base, and like you with this molecules, there are 24 different isomers. So the problem for the organic LED, the research is that which of these is the one that would give you the best performance. So there's a lot of grinding work to go through some of these kind of materials, or you already have some insights which one would work best for you. And going further, one of the major breakthrough in organic light-emitting diode came from this group, Steve Forrest, Mark Thompson's, and the graduate student at the time about Mark Bortles. So that was the beginning of the phosphorescence OLED. All the work that we did so far was based on the emission from the singlet excitons. And so this have only the 25% probability from the recombination of the electron hole pair. We lost 3/4 of it through the triplet. At the time, we did not know, or we were not aware that the triplet emissions were efficient at room temperatures. Most of organic materials are not. At the time that we didn't, well, so they used a iridium PPY as the emitter. The iridium is a heavy metals, which through spin orbital coupling would allow the transitions from the triplet to the ground state with very good phosphorescent efficiencies. And with this discovery, and they have to do a lot of architectures manipulations to get the light to get the device to work properly. They provide a pathway to realize over 100% internal quantum efficiencies. So years later, Atachi, who's a graduate student from Steve Forrest, came up with another class of materials called the TADF, the thermally activated delayed fluorescence. And they can use this class of materials without having the heavy metals, and also provide a pathway to 100% quantum efficiencies. In fact, when you look back in 1969, there's a review. That was the time that the people were working on organic electroluminescence. They already knew that they already observed that the delayed phosphorescence from a triplet fusions, in other words, two triplet molecules, come together and then produce a singlet to give you the high efficiency. But the Atachi's method is that the triplet, they can design the molecule in such a way the triplet is almost degenerate with the singlet, so that they can go back from here and go to the singlet and then come down as the fluorescence. So the efficiency is close. They can engineer it in such a way they can give you 100%. But this triplet fusions can only give you efficiency is about 35%. Now, given all after years of effort in materials, we come to the point that the material and device lifetime and efficiency are long enough, you're ready for display fabrications. So in display fabrications, there are two types of this drive scheme. One is the passive matrix, and one is the active matrix. The passive matrix is very simple. You have the column and the row that just overlapping and then with organic material in between. For the active matrix, the organic device is still the same, but you added two transistors. The one is the control transistor and one is the driving transistors with a storage capacitor. So,
Professor Tang, I'd just like to give you a 5-minute warning in terms of your talk. I don't know quite how many slides you've got left, but I'll
right, I'm going to rush
now.
I'm going to rush ahead. So with this, we have for the passive matrix that is useful for making a simple display with very few pixels. For the active matrix, or you're allowed to make a bigger display with a very high resolutions, like the iPhones. So OLED can compete with the LCD. The LCD is a very complex device. You need the backlight, you need the polarizer and so on. But the biggest problem is that the transmitted light, even if the LCD is closed, you have a leakage. And this one here, and for the organic LEDs, if you can turn off the voltage, it's completely black. And so the OLED can provide a better performance in principle with a simpler and potentially lower cost structures. We tried to do it, we attempt to do the plasma matrix display back in the 1990s, doing in the photolithography method. We failed miserably because we have trouble patterning the top cathodes. All right. So, and then the method that I came up with to solve this problem is so-called introduce an in situ shadow mask, and to allow the deposition of metals without getting a gap in between with this mask in place. And this was patented in 1994, and then pioneered also had the patent in 1997. The first production line for passive matrix OLED was built in 1997, and then the product was the first cell phones and also the car audios. They're all monochrome display, and today you have the passive matrix, which is the quite nice looking, but still very low resolutions. And for the active matrix display, you have the television, the tablets, and the laptops, the watches, and all. And they're all based on the very complicated circuit structures. And the most basic one is 2 transistor and 1 storage capacitor. And the more complicated one, you have a 7 transistor and 1 capacitor, and very high resolutions and very complex, stack architectures with the OLED on top of it. And so that's what you hold in your phone. And for the televisions, we need to have very high brightness and also long lifetime. And you depend on the tandem structure where you stack all the OLED a couple of OLED together, and so that you can produce higher brightness and using a lower current. And the OLED was first introduced in 2013, and using a white color OLED with the color filter and oxide transistors is all made by LG. And OLED also won in terms of form factors, and this is one of the rollable TV from LG, and also that you have the bendable phone from Samsung as well. So I just have 2 more slides, and the OLED is superior to LCD in power consumption today. And this is I can make a comparison between the Samsung Notes and the iPhone 12 compared to the LCD displays. So the OLED now eventually had caught up with LCD in terms of power consumptions. So we have 2 notable innovations in this century, and they're both enabled by display technologies. And OLED OLEDs are beautiful, they play key roles, but they can also be addictive like this. So to finish this talk, I'm sorry it took so long. I want to get back, and this is the place I first started school. The name of this shrine is in Cantonese called Tong Phúc Tong. It's the Commonwealth Hall And this is a brief timeline of the milestones. These two are my own milestones, and the other one are the milestones of OLED. And for me, this is a journey of personal discoveries and shared excitements. And thank you very much for the opportunity to share with you the story of OLED. Thank you.
Thank you very much. I will clap on behalf of everyone watching. So, well, thank you very much, Ching, for sharing your journey, your sort of research life story and the great success there's been. I'll just remind everyone who's watching, please, if you have any questions for Professor Tang, please post them in the box, and then I will relay them now to him. So I will start by asking you, in terms of the journey, you were working in Kodak and you made these discoveries, and you were busily trying to develop a technology, and then you published these papers. What did you expect the result of those papers to be? What was your feeling when you published them? Were you waiting in anticipation? Did you have a sense that this was going to create a growth emergence of a new field and new technological race to get OLED technology to market? Or did you think, oh, I'll just publish that and maybe some people will see the science and find it interesting? What was your sense when you published it?
Well, I want to point out that as an employee in the industrial laboratory, we were not required to publish papers. We were required to write patents. So publishing paper is very much on your own. In fact, they encourage you to spend your personal time writing papers. The solar cell paper that I wrote, it was wrote because I was done with the project, and I, filed patents, and I felt like, it's a good piece of work because the few factors was really quite remarkable, and I thought that is something that is worth publications that people should know about. So that paper published is just out of my own desire to make the results known to the public. But that paper took quite some time to get published, just because one of the materials used was considered to be variable, useful for the electrophotography. And so it took almost 6 years or 7 years to get it out of Kodak. The other paper, the organic light-emitting diodes, was published because at the time that there was some sort of indirect pressure on us, on me in particular, that we should move on from Kodak to do something more, from OLED to do something more useful, because it was we just play with the device structures, trying to improve the stability. We didn't really have an application in mind. We have, in general, the display application in mind, but we have no way, we have no idea whether we don't even know how to make an active matrix, a simple passive matrix display. Not to mention that we don't have any active matrix technology at the time. So, we published that. I published that paper because that again, it's like almost like it's time to finish this and move on to something else. But it turned out that after this paper was published, that it drove tremendous interest from the researchers in countries like Japan, and so that was the beginning of another phase of OLED research.
Yeah, it shows.
And that got the Kodak management interested in OLED as well.
It shows the power of collaborative research, where if you just kept it in Kodak, it may have taken another decade or two to evolve, or may have been put on the shelf. but sharing with the community enabled a lot of excitement and advancement to take place. I've got a series of other questions coming in. They're coming in quite thick and fast now, so I'll just ask a couple of them. So there's one from someone called Ila Verman from India. So we've got people joining from all over the world. And they're asking what challenges lie ahead in OLED research. So what are the key challenges now from where we are? There's a commercial technology, but what do you see as the next breakthroughs in OLED research?
Okay, what made in terms of there's two components here. If in the basic research, the key versus the manufacturing research. In the manufacturing side, you always want to have a better, a more cost-effective process, and that need to be continuously improved in terms of even the shadow masking technologies and the vacuum deposition technology and all that, and encapsulation technology. And the basic side here, we still have the lifetime issues. The OLED is not 100% perfect. Maybe the green, the red light, the red OLED, the green OLED is long-lived enough for all kind of applications, but the blue OLEDs are not. Okay, we have to somehow use schemes to prolong the life of OLED. Like for instance, we have to make the OLED pixel a little bigger than the red and the green pixel so that it would last longer. Or we have the electronic compensations. So if the pixel dims, we can jack up the current a little bit to make it a little brighter, all right? So that it would last over the length of the time of applications. So the one of the key we're still doing it in our lab is to figure out the instability of the OLED devices, particularly the blue OLED, particularly the phosphorescent blue OLED. You still don't have a very long-lived phosphorescent OLED. So anybody can solve that problem. It would be another, major breakthrough.
So related to that are the TADF molecules, these non-phosphorescent, well, I guess it is phosphorescence, but the non-heavy metal complexes, the TADF molecules, do you think they are the path to high stability blue emission, or are there challenges with getting blue emission from those molecules as well?
Well, I don't know whether they have basis to say that they would have a better stability compared to our current set of materials, just because I haven't talked in this presentation that one of the key issue is the carbon-nitrogen bond dissociations in the organic materials. And if that bond is roughly about 3 electron volt, then if excitation energy is higher than that, you might run a chance of having that as a fundamental stumbling block. And the TADF material, they do have that, carbon-nitrogen bond all over the place. As you know.
It's the definition of organic semiconductor, organic material.
Even though there's not a lot of material research in the academic community on organic light-emitting diodes, but in the industry, they're still, working very hard to come up with the best materials.
Mm-hmm. Okay, so I've got another question from someone called Wenbo Lee, who, if I paraphrase what they ask, basically in the early days, the stability and efficiency of OLEDs looked relatively poor compared to LEDs or compared to the liquid crystal display. So what kept you going? What kept you motivated to keep researching in this area?
Well, I think there's a steady improvement in lifetime and efficiencies after the 1987 paper. I was quite aware, that the lifetime is not sufficient for practical applications. What kept me on was that, we know that for some applications, for TV it would be the lifetime is in the 50,000 hours. For the cell phone kind of application, the lifetime can be, virtually shorter.
Mhm.
So there's a possibility you can get into certain applications, with the current set of material. That's exactly what happens when we try to introduce the OLED display in the camera in Kodak in 2003. So the camera, they use it only to check the images. So the lifetime is not really that important, and also that the efficiency is not terribly important at the time. We of course always like better efficiencies, but for the application, it's fine because you don't worry too much about using the display all the time.
So you're encouraged by the range of applications, the sort of
exactly
to start the technology.
Like today, I mean, you have an application like the virtual reality, and OLED is perfect for the applications.
Yeah. Okay, so I mean, another question I have, which was related to stability, when any new material is put in an electronic device, usually it's unstable. I don't think there's any examples of things operating stably, but your first devices had lifetimes of less than 100 hours. And there are reports of some OLED devices that will last for up to 100,000 hours.
Yes.
What have been the key steps there? What have been the key developments going from this structure that you started with to the commercial structure? What's been critical for stability with these materials and devices?
One thing that we all know, and maybe still maybe somewhat of a trade secret, and that is you have to get rid of all the oxygen and water. That is absolutely critical, because that can introduce to chemical reactions.
What is surprising to anyone is that you can have these phones with OLED displays. And I mean, my phone is very cracked and it still works. It's been cracked like this for about a year. So, I mean, the encapsulation must be good enough that it,
yes,
I mean, the encapsulation technologies basically, or
the absolute, it's amazing how good is the encapsulation technology. They have the water transmission rate, I don't know, down to a number that's incredible. I mean, that's I think that's one thing. I mean, if you can, eliminate oxygen and water, a lot of organic material can survive.
Yeah. Okay. And then
that says the same thing about your solar cells too.
Yeah, certainly. Well, this is the inspiration for the research that we do on new solar cell materials, is that you can take something from being very unstable to make it very stable, and the OLEDs is a first demonstration.
Right. You look at the OLED, the stability improvements. For instance, for the blue OLED, I mentioned about the commercial blue host materials. They're all hydrocarbons, carbon-hydrogen bonds. There's no carbon-nitrogen bonds. All right. So that is critical. So they can manipulate the morphological stability, and they can encapsulate those materials are rock stable. And furthermore, now they apply so-called the isotope kinetic effects. They substitute some of the molecule with deuterium, and that they give it another boost of lifetimes.
Okay, very good. So we're getting all the trade secrets here as well, which is wonderful. Stuff that you don't necessarily find in the published literature. Okay, I think we're getting quite close to our time, but I think we've probably got time for a couple more quick questions. There's someone's asking what material is used in thin film transistors in active matrix OLED displays. So they're wondering, is the active matrix in an OLED display, is that also organic semiconductors, or what is the material used?
No, there's only two kinds of material used as transistors for OLED. One is low temperature polysilicon, which is a standard material You find it in your iPhones, the OLED phones. And then you have the oxide TFT, the ICGO, oxide TFT, which is used in all televisions.
And of course, the oxide TFTs has been another great, relatively
the oxide
recent
TFT is
story.
another big invention. I think it's invented for OLED.
Yeah.
So organic TFT, the performance is just not ready enough for OLED applications.
Okay. And well, I think we're probably about there on time. Is there anything else you'd like to share, which I tried to rush you on your talk? Is there any last comment or statement you'd like to give to the audience, either to inspire young researchers or about the technology? Is there any last statement you'd like to make? I'm putting you on the spot.
Well, if you look at the timeline of the OLED, from the discovery to commercializations, it took 30 and now almost 40 years. It's a long time, right? So at the beginning, we work on the materials, and we don't know what we were doing at the time, and we just keep grinding it, and then suddenly we discover the two-layer system actually work, and that was a good discovery. But in fact, a two-layer system is nothing more than a PN junction that we know in the classic semiconductors. So we just borrow it and use it for organic electronics. And so what I am saying here is that the discovery, a lot of time is keep working on the problem, a worthy problem. Don't give up. And well, I have to take it back. Sometimes you have to give up because you hit a roadblock, but then you know where to branch to. I think that's important.
Yeah.
Okay. But then you took the knowledge from where you failed and apply it to where it could succeed. And I think that happened in the OLED all the time. I remember that when I said, okay, I want to make a display now, I had to go out and learn something about the transistors. But I did not take organic transistors. I can work with somebody on using the low temperature poly, and they turned out to work quite well. So,
you use things that work in the first instance.
Right.
Okay.
So,
well, thank you very much. I think the resilience in research and science is very good advice, and also the sort of making it very clear that you don't make these phenomenal discoveries overnight. They take many years of dedicated effort, and I guess being the curiosity that drives you forward also keeps you very interested. You have to enjoy the discovery and the investigations almost for the sake of the science itself, and then the technology will advance.
I have to say that everyone enjoys discoveries. It's really the grinding part of it. After the discovery, that you still have to work very hard to get it to make the things better, and so you have to be persistent, like you said. The resilience to make it work.
Well, thank you very much. So I'll just thank you on behalf of everyone who's listened in once more, and it's been an absolute pleasure discussing with you as well.
Thank you very much. Bye.
Bye.
And in a final word, let me just pass my warmest thanks to Professor Henry Snaith for moderating this first of the Kyoto Prize at Oxford series, and our warmest congratulations to Professor Ching Tang, winner of the 2019 Kyoto Prize, and thanks for his wonderful lecture today. And thanks to you for joining us today online. And let me just close with a slide that gives you the details of the rest of today's Kyoto Prize at Oxford lectures and events. Thank you all.